Hi, everyone. Welcome to the online causal inference seminar. So today we have something a little bit different, a little bit special. So we have a tutorial from Fan Li from Duke University. It's a tutorial on Bayesian causal inference. We have also two panelists ready to take your questions in the Q&A and maybe discuss things further. So we have Peng Ding from UC Berkeley and Fabrizia Meali from University of Florence. So we look forward to your questions and the discussion. And Ying is taking care of the questions, so I'll switch over to her now.
Thank you, Emma. So as usual, please submit your questions at any time through the Q&A section. If you haven't used it before, it is just a button at the bottom of the Zoom window. Please submit through the Q&A instead of chat for us to better track the questions. So that's it. So I think the stage is yours, Fan. Please feel free to get started.
Thank you. Thanks, Ying and Emma, for organizing this, and also thank Peng and Fabri for being the panelists. So today I have quite a lot of stuff to share, so let's get started. Hold on, like this. Okay, just so you can all see it, right? Okay.
Yes.
Okay. So this is a tutorial. This tutorial is based on a recent review paper we wrote that is to appear in the Philosophical Transaction of the Royal Society A. It will be a special issue on Bayesian inference, and so this is already up on archive. So we just finished the revision, and so again, this is a vast topic. So today I have like maybe 50 minutes try to give the key point of this area. So feel free to ask questions, and my Peng and Fabri will answer your questions, and hopefully we will have some time in the end to discuss. So again, I need to give first set the stage. I will quickly go through many of the concepts that I assume many of you already know about causal inference because of the set the stage, and then we move to the Bayesian part. So first, of course, we proceed under the potential outcome framework. And then the goal is to evaluate the effect of treatment or cause on an outcome. So what the data look like, it's pretty standard. Is we have a random sample of n units from a population. And then we have a treatment, say binary treatment, and then we denote by z, 1 and 0, 1. And for each unit, we observe the treatment status, z, and a vector of covariates, and an outcome. So of course, assuming the suitable assumption, then each unit has two potential outcomes. And then from now on, I will use this bold to denote the vector because that is later useful when I describe the formulation. So of course, causal effects or causal estimands is just the contrast of this individual potential outcomes. So the common ones, again, this is a walk in the park for most of you. So first is the individual treatment effect, ITE. This is just y1 minus y0 for each person and for each unit. And then we also have conditional average treatment effect. So that is just the y1 minus y0, but expectation of that, expectation of that in a target population, the subpopulation with the same covariate value at x. And now, of course, when we average over the Kate over a whole population, the space of x, then we get the population, the PET population average treatment effect. So just a note that the ITE and the Kate, obviously they are two different concepts and the different estimates. They are numerically also different. And both of them are important to characterize treatment heterogeneity. But what I noticed is that in the machine learning literature, people often conflate this two. It's just to point this out. And today, we are most time we will when we talk about the heterogeneous treatment fact, we actually most time deal with Kate. Just a reminder. So of course, the fundamental problem of causal inference is that each person we observe only one of the two potential outcomes, and that the other is missing. So causal inference under the potential outcome framework is essentially a missing data problem. So we often say this, but in the frequentist domain, we actually don't take this too seriously. I would say that, like, don't take, but in Bayesian, this is really important, because in Bayesian, we really treat it as a missing data problem and then impute, like often we go to impute the missing potential outcome. So of course we, because we miss at least half of the data, we need additional assumptions to do causal inference. So this talk mostly we're focusing on the ignorability assumption, and which can be extended to many different cases. That is, ignorability assumption has two I call this, there are different names for this, but so in this lecture, I would call this two. So we all know sometimes you know as a strong ignorability or ignorability, but here we say we call it ignorable assignment, which consists of two sub assumption. The first is unconfoundedness. Basically, there's no unmatched confounding. The second one is overlap or positivity. So these two assumptions, again, together, I call it together ignorability. Again, the name ignorable is actually very interesting. We use it all the time, but it's particularly meaningful in the Bayesian context. And I use this to jointly refer to both. So of course, propensity score is just a probability of the person a unit get treatment given the covariates. And so under ignorability, why ignorability is important is because under ignorability, we can identify we use mu to denote the potential outcome distribution at arm z. So then this potential outcome distribution essentially can be identified by the marginal distribution of the observed data. So that's why it's important, right? And because of this, then you can just identify Kate from the marginal distribution, conditional on at the one value x, and then the pad is the same. You can also identify from the observed data, right? So then this identification result underline estimation is a so-called outcome modeling estimation strategy. So what you do is you just build a model, specify a model for this distribution, for the distribution of y given z and x. And then you build a model, and then you fit the data, you fit the model to the data, and then you can just estimate Kate or paid or the paid. So it's all the relatively straightforward. And so now how about Bayesian? So Bayesian, of course, the dogmatic Bayesian is you have a model, and then you have priors, and then you use the Bayes rule and get the posterior distribution. So but here in causal inference, it's slightly more complicated because we do have this missing potential outcome issue, right? So then let's take a look at how do we deal with causal inference from Bayesian perspective. So the first, every sample unit, there are 4 quantities, y1, y0, z, and x. So 3 of them are observed, and 1 of them is missing, the missing potential outcome. So also you can see that given z, there's a 1-to-1 map really between the observed and the missing potential outcomes to y1, y0. So this is all pretty simple. So the key thing is Bayesian inference would view all of these quantities for all units as random variables, right? Then you build a model for them, and then derive posterior inference. So the key thing is then you have those missing potential outcomes. So the missing potential outcomes were just drawn from the posterior predictive distribution of those missing potential outcomes, and they are viewed no different from unknown parameters. Okay, so that's how the overall view. And of course, now we're getting to details how we build the model, what kind of model we need to build, and how we build the model. Okay, so we will assume the joint distribution of the random variables of all the units, all of them, is governed by generic parameter theta, and the theta divided into several parts, conditional on which those random variables for each unit just ID. So just look like this. again, they look like this. So the key thing is next is this bullet. So now we have this joint distribution, right? So then you can factorize, we can factorize this joint distribution into components that easy to deal with. So how do we do that? This this factorization was first proposed by Rubin in the 78 paper, Anna's paper. So you can see that this part is assignment mechanism, basic Z, how you assign the treatment. And this one is given X, this is outcome, essentially outcome model. So the Y1, Y0 given X. And the last is the X itself. So you can see that our joint distribution of those potential of all of these random variables will factorize into 3 parts. And that's assignment mechanism, outcome model, and the X itself. So of course, under the ignorability assumption, we know the assignment mechanism, the Y1, Y0 will drop out from this, and this will just become our old friend propensity score, right? So before I further go into say how I'm gonna do analysis, we will have a bigger slide about actually we'll talk about what kind of estimate we're really talking about. They're actually different, turn out to be different versions. Remember, I mentioned the PATE, the population average treatment effect, right? But it's actually interesting, there's several versions of this average treatment effect. So first one is this so-called sample average treatment effect. So strictly definition is this sample average treatment effect is just the average of the ITE in a finite sample, okay? And then this one actually, because both Y1 and Y0 both are in this, so it actually depends on the association between Y1 and Y0. Okay, and this is often the target estimate in traditional entire estimate in randomized experiment. And what do? You need to, so if you look at this is basically, you have a finite sample, right? You have this, you have a finite sample, and then basically the set is something, is an estimate that is only involves the potential outcome in that sample alone. It doesn't involve any population. But then of course, we're missing half of them. So the Bayesian inference for set would require specifying model. And again, I will talk about what kind of model, but then to impute this missing potential outcome for all the units in this sample, and then you calculate that. So now back to PATE, when I first already introduced, but now we can rewrite it a bit, because we remember here I already introduced the concept of the parameters, like this, all of the, so the thing is like the outcome model has governed by parameter, they ignore, so the assignment mechanism also have a parameter, so they all have parameters. So now let's go back to see PATE. So PATE, so this tau is just a Kate at the Kate is a Kate at the value X, and of course now it is governed by a parameter outcome. The parameter for the outcome model, I call it zeta y. So what is a PATE? PATE essentially is just the average. It's an integral or average of those Kate that is integral over the whole parameter space, the whole covariate space. The whole covariate space. So this is important. So this is F. This is a distribution, this is a CDF of the covariates. So the covariates is also, if I go back here, because covariate itself also has a distribution, right? And then this F is basically the CDF of that, of the covariates. So now let's look at this. So PATE is a function of the distribution of potential outcome in a population. So remember, corresponding to set, we say that it's really just average of the ITEs in a finite sample. So a finite sample, it doesn't extend to a population, but the PATE is about a population, okay? And then it depends on, so PATE, if you look at that, it depends on 2 parameters. One is for the outcome model. The other is the parameter govern the population, the distribution of the covariates in the population, right? And now also, if you look at if you look at PATE, because the definition, if I go back here, if you look at PATE, you can see that PATE is basically, you can write it as the expectation of mu1 minus expectation of mu0, because this additive thing, it doesn't depend on the margin, it doesn't depend on the association between y1 and y0. So that's a major difference between PATE and SATE when we do calculation, right? And then so then Bayesian inference for PATE is easier, because it just requires, as long as we obtain the posterior distribution of the parameters, there's two parameters, theta y and theta x, we can proceed. We don't actually need to physically impute those missing potential outcomes. Okay, so then this is a third one, which we kind of explicitly pointed out in our review paper, is that in reality, you have everyone has a large covariate. We have maybe a high dimensional covariates. It seems to be, it's almost a nuisance that, we want to model this thing. We model this distribution of X, right? And particularly if you're Bayesian, you condition on everything. So if you're Bayesian, you will choose to very naturally condition on X, right? So what people actually, in practice, many Bayesians do is they actually replace this distribution of X by is just a empirical distribution of the covariates. In other words, we're basically conditional on X. Okay, so this is actually done implicitly in many Bayesian causal inference papers, but it was not pointed out. So actually, what we're really doing here is when you conditional on X, the estimand we are talking about is a hybrid between PAT and SATE. So we call it MET. So it's hybrid, it would be hate, which would be a really terrible name. So it's a MET, and so MET is the same thing as before. It's just a Kate. It's a Kate we average over, but instead of using the population distribution of X, we actually just use the empirical distribution of the covariates, essentially conditional on that. So this becomes the form of the mate. And again, there's a subtle difference. So mate is the average of Kate, and the SATE is the average of ITE in a finite sample. So there is subtle, right? And then in practice, mate is a convenient approximation of PAT. So it's actually often done, as I mentioned earlier, implicitly in Bayesian inference. And so just show you what the difference really between those, give you a simple example. Just consider a complete randomized experiment with continuous outcomes. So life is easy. So then we can assume a bivariate normal model for the joint potential outcomes. So that's Y model, right? So it looks like this. Again, this is your simplest bivariate normal distribution. So this model essentially, outcome model essentially implies two univariate normal marginal distributions. Looks like this. So this simplest model you can think of. So now let's write out the estimand. So ITE here would basically be beta 1 minus beta 0 times xi. And the Kate would just be, again, any x you put here. And then SATE is this. I mean, this is just a definition. But the interesting thing is the difference between mate and PAT here. You can see PAT is beta 1 minus beta 0 times expectation of x. But mate is just to replace the expectation by x bar. So that's kind of the difference. Again, this is a simple case, but to show you that the practical difference between them. And so now let's talk about Bayesian. I just give this big aside on what the different type of estimands. And this is in practice, the difference between all of them are relatively small, like SATE and MET and PAT is very small, but conceptually it's important to differentiate between them. So now I'm going to talk about Bayesian. How do we practically do the inference? And I'll skip this page because it's good to directly get to the detail. So if we want to do Bayesian causal inference, another big assumption you have to make is, other than ignorability, is this prior independence. And this basically say that the parameters for the assignment mechanism model, for the outcome model, and for the covariate model, they are, so these three parameters, they are a priori distinct and independent. So this looks very kind of, it's a very kind of minor, my view as a very minor assumption. It turned out to be that actually quite important, particularly in high dimensional. This can introduce some undesirable consequences or unintended consequences. We'll talk about that later. But for now, let's assume the prior independence. So if you have prior independence, of course, the next thing is you can just impose separate models for for each of them, right? And then earlier I already wrote, and now you have, then what do? You have your model, and then you write down the likelihood, and then you get the posterior distribution of this parameters, and that's all you need. So let's look at this under ignorability and the prior independence. Remember earlier we already factorized our likelihood. So now it just looks like this. This looks pretty complicated, but the key thing is, let's look at this again. This is just the previous factorization. Now I'm throwing the prior distributions, right? So remember for PET, the PET is earlier talk about PET depends only on theta y and theta x, right? So you only need to, so the Z, this part, the assignment mechanism actually doesn't really contribute anything to PET. Okay, so because of that, the propensity score, so this guy, this whole thing can drop out from the whole posterior distribution, right? That's why actually the name ignorable. That's interesting. In Rubin's 78 paper, he called it ignorability. You know, that's why I say that is from Bayesian perspective. The name of ignorability sounds very natural, but in the if you're frequentist, your propensity score is a big deal. Then why is it ignorable, right? This is kind of just a historical note, historic note here. And then, of course, then let's talk about different estimates, how we do the estimation. The PET and MET, because they do not depend on the correlation between Y1 and Y0, and the SATE does, right? So then to infer PET and MET, we can just what we can do is because they don't depend on the association, we can just specify marginal models. We usually just, instead of even a bivariate normal distribution as earlier mentioned, you just specify those marginal models. And once you have these marginal models, you can just calculate the likelihood. The observed likelihood would just become, you go to the treatment group and then calculate the likelihood, and control group in the control the likelihood, and then just the product of the two. That will be your likelihood. And then you impose a prior. You impose a prior for theta y or theta, well, actually also theta x, because if you want to do PET, then you have to also deal with the sorry. If you want just to mate, then you can just impose a prior for theta y, because you're already conditional on x, so you don't need to worry about that. You can just proceed to infer the theta y using the Euro-Bayesian inferential procedure, for example, keep sampling or data augmentation. Essentially, I'm not gonna talk about the details. So for PET, of course, we have this one additional thing you have to worry about. That's the model for the X, the model for the covariates. But as we mentioned, that it's you know, if you really want to be pure, then you do that. And then some people, there are some authors say that you can just use a Bayesian bootstrap step to draw X from, you know, to draw from the distribution, and then the question is, how do we combine that posterior draw of X with the inference of the outcome, of the potential outcome, right? So our own view is you can do this, but we don't particularly see particularly in high dimensional case, we don't see this is a general procedure. The Bayesian bootstrap can give you X distribution, but we question why you have to do that. Because so I will mention that just a little bit more later. So this is about PET and mate. But for SAT, because it depends on the association between Y1 and Y0, it's more complex because you not only need the posterior sampling of theta Y, you also need this Y miss, the missing potential outcomes themselves. So what you do is you then gonna have a kind of bivariate distribution as we just specified in the example. Then you plug in the imputed missing potential outcomes, and then you plug in things. So once you have Y miss, of course, you can just plug in whatever estimand, and then you get it. So the key thing here is the uncertainty only comes from imputing. Imputing a Y miss. Again, this is so overall, just in general, if you look at the three in terms of posterior distribution of the estimand, the PET has the highest uncertainty because it also comes from the sampling from the X, and the mate and the SAT is the smallest because the SAT is is only on a sample. So the mate is in between. But my own experience is the numerical difference between all three is usually pretty small. So that's why I think people get away and pretty happy with just to calculate the mate in most of in practice. So now that gives you an overview of, okay, what kind of model you need to build. Essentially, you need to build a model outcome model, right? Then you need to impose a prior. And if you care about mate, then this is all you need. Well, of course, under the assumption of the prior independence and ignorability. And then, so now the central task in Bayesian causal inference, particularly if you care about Kate, then it becomes you specify an outcome model. Specify basically this model. Now I call it the mu x z. So this model. So what kind of model we're gonna have? Or we usually have there are two categories. Just to use the name by a paper by Causal. It's because you can do this so-called single learner. Essentially, build a single model that for this outcome model. So in the simplest case, it would be something like x plus z plus x times z. You have the interaction term. Or you can also do this kind of two learners, essentially build two separate models for each group, right? And so for linear models, the single learner and the two learners, especially if you have an interaction term, they're equivalent essentially. But this is not the case if we use nonlinear models, more complex models like tree models type of thing, right? There's actually the same type of models using single S learner or T learner, you might have very different results. So there are many popular, especially now when we talk about in the recent years, there's many flexible model choices for this for mu, and then frequently you can use splines, you can trees and neural networks. But in Bayesian, the most popular are the BART. And then also, of course, you can use Gaussian process and different process. So I want to particularly mention a little bit about BART. BART is it's kind of Bayesian version of random forest. It's an ensemble of trees. And again, we're not gonna give in detail. So BART. So Jennifer Hill in the 2011 paper, so she's the first one actually to propose to use BART model to build this, single the S learner in this case, and then to use this to calculate Kate. So this is, again, it has many good advantages, and a very important extension of the BART work for causal inference is the Bayesian causal forest paper done by Hang et al. In 2020. So their key insight is the key insight is actually to reparameterize this outcome model into two parts. The first part is this is essentially viewed as a baseline distribution for Y0. And then add a part. This part is essentially this G2 thing is kind of your heterogeneous treatment effect. So the other was the idea. So their main idea is, the outcome surface might be complex, the Kate surface, the difference between y1 and y0 might not be as complex. So at least the point is the complexity of the baseline distribution and then the heterogeneous treatment effect might be different. So then they allow, based on this reparameterization, they allow separate, they impose separate bar prior to each of this model. And so because there are two trees, then become a forest. Well, I don't know whether two trees is a forest, but that's where the name come from. Okay, so that was the idea. And then like BAR has been very popular because the advantage of BAR there, the relative fast computation, you know, in the Bayesian domain is pretty fast. And also they find the default hyperparameters works pretty well. So that in a sense avoid hyperparameter tuning, which can be really a nuisance for applied researchers. And it's relatively good scalability, but still, I don't think that is as comparable to the frequentist models, but those are already very stand out in the Bayesian non-parametric models. So this is the main type of, you know, models now in Bayesian where people use to do Bayesian causal inference. So after all of this, I think then there's a point getting to a central debate in the role of propensity of Bayesian causal inference. So we're almost entering a paradox. As I mentioned earlier, you know, under ignorability, again, now we move from, I just talked to you about the general structure of what kind of model you need to build and how do you build a model and, you know, how do you link from model to those estimands. Now I'm moving gears, I'm shifting gears to this more conceptual point of view of, you know, they call it a fundamental debate in the Bayesian causal inference. It's about the role of propensity score. So as we mentioned earlier, under ignorability and the prior independence, the propensity score will drop out from the whole calculation, right? So it's like, that's why actually the name ignorability comes from. On the other hand, if you read Rosenbaum-Rubin's 93 paper in propensity score, the name is the central role of propensity score in causal inference. So obviously under the frequentist domain, and you have vast empirical evidence that propensity score play a central role in causal inference, then this seems to be, but Bayesian say, hey, it's ignorable. So then how do we reconcile this paradox? So I think it's important to understand there, you know, causal studies usually, we call it, use Rubin's you know, terminology is causal study usually involves two stages. The first stage is so-called design stage. Again, design is pretty broad, but here we basically mean that the stage that does not deal with any Y. And then the analysis stage is a stage that deals with Y. And Bayesian, if we go back to look at the Bayesian outcome modeling, essentially there, you know, under all these assumptions, seems that only involves the analysis stage, right? Because you just need to build a model of outcome model. So then where does this design stage factor in? Because obviously if you do causal inference, whether you're frequentist or Bayesian, particularly if you're you know, frequentist, the first stage we spend a lot of time to matching or to weighting so that we come up with a sample that, you know, a situation that the treatment group and control group look very similar. In other words, they're very similar to a randomized experiment. But in Bayesian, that doesn't seem to, like, just if you just look at the procedure, it doesn't going anywhere. That part. So that's what this is interesting, very important observation. So overlap, the concept of overlap or balance plays a prominent role in design stage in the frequentist domain. So how about Bayesian? Where does those concepts come? Where do those concepts go in the Bayesian causal inference? Okay, so now from a design perspective, so the key thing is, remember, if you're Bayesian, then you do an outcome model. If the model is correctly specified, the posterior distribution of theta y is correct, then would be correct, and that's all we need for causal inference. So however, we all know that outcome model is really correctly specified, even in the moderate dimensions. So then Bayesian inference is about, you know, we have two samples. they should, you compare their counterfactuals. So then, if you have a study, say observational study, then you have pretty poor overlap. So the treatment group and control group look very different in their confounders. Then in the region that you have very little overlap or poor overlap, so you can still build a model, right? But what your model really does, you do a causal inference, essentially is based on extrapolation. So this means that, in the region of poor overlap, your outcome model, you can come up with the outcome model and then do posterior inference, but it will be very sensitive to the to the model specification. And also you might also fail to quantify the uncertainty accordingly, because obviously if we have poor overlap and everything's dependent on extrapolation, then you would expect that your Bayesian model should adequately reflect the large uncertainty in those regions, right? But if we specify a model, you can write down your favorite model based on non-parametric model or any model. The model itself will never tell you anything about the overlap degree, the degree of overlap or balance. So that's where this gap, like in the Bayesian causal inference, if you just look at the outcome model. So then how do we improve? So the question is, how do we improve the robustness of the model, specified model, right? So there are two different aspects. So from the design stage, that's what frequentists very used to do, is you want to ensure good covariate balance to begin with. So in the most extreme case, if we have randomized experiment, then of course treatment group and control group are well balanced in everything, even in the unmeasured confounder. So Ling has this very famous paper show that in this case, even the misspecified outcome model will lead to consistent estimate of SATE. And our advanced experience is that if you have randomized experiment, it doesn't matter whether you're Bayesian or frequentist or you are doing marginal weighting the result or double robust the result, all similar. Why? Because the data has so good overlap, everything's balanced. So there's doing model is just probably give you some consistent efficiency, but it's not too important. So then of course, if observational study, we don't have this luxury, but we can use marginal weighting, those kind of tools, without even looking at Y to make sure that my data is as close as to a randomized study as possible. So if I achieve that, that will definitely help to make my model more robust, because if my data is very close to a randomized trial, it doesn't matter what kind of model I use, right? But so that's from the design stage. From the analysis stage, of course, is you want your model to be at least more flexible, so give more choices rather than just a linear model, right? So if your model is more flexible, then it's more it's more likely to avoid model misspecification, but still it's a tall order. And also the model should adequately quantify the uncertainty according to the degree of overlap. So that's the first consideration. And second consideration is just, why don't we just directly incorporate the propensity score in the outcome model? Because propensity score, we have an outcome model. If you look at the outcome model, it's just Y1, probability of Y1 given Y0 given Y1 and Y0 given X. How about putting propensity score directly into that? And that is indeed what is done in the literature. So there's at least 3 different ways of doing that. So the most prominent approach is just to add a propensity score as an additional covariate to the outcome model. So basically specifying this outcome model mu xz, you add a propensity score there. And there are actually several different specifications of that. And normally, you can, so some like little n has recommended to build a model and then have a panelized splines of propensity score and stuff. So there are many different approach of this, but back to the Bayesian random forest idea, Bayesian causal forest idea by Han et al. they remember earlier they did this reparameterization. Say you build a model for the baseline, and then you build a model for the heterogeneous treatment effect. So here they showed empirically that adding the propensity score in the baseline model is very, very helpful. Vastly improved over you just have GX alone. So this is their approach. And so again, there are many different approaches, different ways, different reparameterization, but the idea is add the propensity score as additional covariate. And how do you implement that? Usually it's done in two stages. First, you estimate the propensity score, use a separate model, and then get the estimate, and then plug in the estimate propensity score model just as like a observed covariate into the outcome model, then you're done. Okay, so before I talk about that, let's just give a little bit more idea, like just look at this a little bit closer. So the outcome model look like this. So what is doing is almost like at each value of X, the propensity score, you are conducting an outcome regression, Z and X, right? So I think that this is almost like a Bayesian analog of double robustness in this sense. So first of all, if your outcome model is correctly specified, then if your outcome model is correctly specified, sorry, I missed a Z here. The point is that then the propensity score as a function of X is just redundant, right? So this whole model, if this is correctly specified, this model just reduced back to the, without E, okay? So fine. But if your model is misspecified, remember the idea is we know the propensity score has this balancing property, right? Essentially at each value of the propensity score, the treatment group and control group would look similar in their covariance distribution, just in general, right? So then if the outcome model is misspecified, the idea, the hope is that, given the same value of E, at least the model, because the groups are balanced. So then you do this outcome regression, it will be less sensitive. So again, this is just analog. This is not a proof, but this is essentially, this is adding the propensity score as additional covariate in this kind of setting is doing is a kind of Bayesian analog of double robustness. So this is all nice, and people have shown empirically that it improves the result, but there are controversies. Two controversies. The first one is if you are a dogmatic Bayesian, you feel uncomfortable. You feel uncomfortable about first estimate propensity score and then plug in. As a good old Bayesian, what you would do instead is you will simultaneously build a model for propensity score and outcome model, and simultaneously draw the posterior inference of the parameters from both. And this will have some feedback issue, like some technical issue I'm not going to talk, but this is, again, the Bayesians, that's one issue. But a bigger issue probably is raised by Robinson. Several people say that, hey, if I look at my outcome model is outcome model generating mechanism, why it should have anything to do with how I assign the treatment? So that's the conceptual issue, right? It's like, this is my outcome model, but how I'm going to assign which unit to get which treatment, why have that have anything to do with how my outcome model is like the true outcome generating process? So that is a conceptual uneasiness. Again, I personally don't find that bothering, but I don't have much time to discuss that, but it's just one point there. And the same idea actually had been used in survey literature before. People use propensity score or the weights of the survey weights to assist their model. So this is nothing new here, but I don't have much time to discuss that. Anyway, the second approach is, remember we have this key assumption of prior independence. Basically say the parameters for the three different models are priori, distinct, and independent. And so, well, that doesn't seem to be reasonable in many cases. So then people say, why do I just actually forego that assumption? Instead, I will specify priors for the outcome model that will be dependent on the propensity score. Okay, again, there are many different there are many different cases or examples of proposals for that kind of thing, and don't have time to go through that. This is all, most of those papers or those priors are very elegant, very elegantly built. The only problem is that there's such specification of such priors is very case dependent. There's no general solution. So that's why everyone have a new prior and write a paper and I'm done with it. You never see that. It's not like a Francis score approach. You can just use the generalize. So that's kind of an issue with this method. The third method is, it's kind of motivated from the double robust estimation. Remember, I didn't talk about double robust here, but we know double robust to have this formula, and then they combine the weighting IPW and outcome model, right? So the idea here is that you choose to build a separate model for Bayesian model for the propensity score and for the outcome model, and then you draw the posterior draws from both models, and then you use the double robust estimator to combine them. And so that's just a plug-in method. And so it's very easy to implement, and they can have flexible choice of models, and you can have proper uncertainty quantification. The main problem here is, again, if you have pure Bayesian, you feel that what is this? This is not the dogmatic Bayesian at all. So those are the kind of three different approaches. Again, the first approach is probably the most widely used one, and still have some controversies. So I probably have 5 minutes. I try to 5 minutes to run through the high dimensions. The last section of this is we all know that when you have high dimensional data, bring additional challenges, and then there are actually at least 2 different type of high dimension regimes. The first one is when you have the model itself is high dimensional, like Bayesian non-parametric model themselves have a lot of parameters. And the second one is just you have high dimensional covariates. You have a lot of covariates. So model applications usually encounter both regimes. Again, not just from Bayesian perspective, the key feature of the Bayesians have quite a lot of different ways, different priors specifically to the high dimensional regime. The key feature of those methods essentially is to you do regularization, but instead of penalty as in the frequency domain, the regularization is imposed through an informative prior on the parameters. So for example, the Bayesian non-parametric prior or the sparsity spike and slab priors type of things. Okay, so then what is the specific kind of challenges or issues specific to causal inference is so how do you choose a prior for outcome model, whether it's you have large P or small p? We already mentioned that BART is very popular. You can also use GP and DP mixture, all that kind of thing. But then people say, which one is to choose, right? BART, of course, has been successful in many cases. But this is still not a panacea. It still often have issues. So back to causal inference, the most challenging cases in causal inference is the region with lack of overlap. And well, you can say that all methods do poorly there, but at least if you're Bayesian, you want your uncertainty quantification to be at least accurate there. So it's important that a prior should accurately reflect uncertainty for various degree of overlap. And so I don't really have time to go through this example, but the point is that the tree-based priors often doesn't have the flexibility because it assumes the same tree structure everywhere. So it will actually, when you have lack of overlap, it will still underestimate the uncertainty in that region. So that's all I can say. And then there are other models like GP actually will do better because it's more like local smoothing, but GP has its own issues and stuff. So I don't have time to talk about that. That's in the paper, but the point is that the choice of prior is important. And the second important point is that in the high dimensional regime, Bayesian after doing the Bayesian regularization on the nuisance parameters, like sometimes we don't really care about most of the variables, but you do the Bayesian regularization. So on those nuisance parameters in a causal model actually can induce bias itself So this is so-called regularization-induced confounding. But what is more precisely was pointed out by Antonio Dinaro in this last year's papers, what he calls the so-called the prior dogmatism. So, okay, what does this mean? So he just defined the selection bias as the marginal difference, the difference between the marginal distribution of outcome and the potential outcome of that given that Z, right? So this is called selection bias. So what he showed that is that if we assume prior independence, this assumption looks pretty simple, looks pretty reasonable, and innocuous. Actually, under this prior distribution, this assumption, standard prior shrinkage, the standard Bayesian shrinkage prior, for example, spike and slap priors for the outcome model and for the propensity score would somehow surprisingly lead this selection bias to sharply concentrated around 0 as P increase. So it's so sharply concentrated to an extent that eventually, even if you have a large amount of data, it will not still overcome this high concentrated prior. So this is an example, and this situation gets worse as your dimensions increase. Okay, so like this is just very sharply concentrated. Anyway, the key point is that the prior independence assumption acts almost like an informed prior. It's no longer just this convenient assumption there. We have to proceed with the Bayesian causal inference. It's actually turned out when you have high dimension, when you do Bayesian regularization, itself become an informed prior, which actually often defies our, what the reality, the data says. So this essentially, theoretically, is a Bayesian analog of the Robbins-Rittel high dimensional problem. And so the claim, again, I need to figure this out, but the claim is adding the propensity score to the outcome model can mitigate this problem. So here we are. Sorry for I delivered most of I want to say here, so there's just some summary. So I like this quote very much. Dan Rubin in 2014 mentioned that, any complications that creates problem for one form of inference create problems for all forms of inference, just in different ways. So the point is that whether you are frequentist or Bayesian, causal inference has its set of own problems. And the big problem is the fundamental problem of causal inference, which is, we have half of the data missing, right? So then, frequentists have met some problems, and those problems will appear in the Bayesian domain in maybe different ways, but they will not vanish. So then what is special about Bayesian plus causal inference? So we mentioned first is this paradoxical role of propensity score, and then we mentioned how to reconcile that. And then, of course, in the high dimension cases, you have the regularization, and then you have prior dogmatism, or this kind of issues. And in the frequentist domain, actually, we have similar issues, but just different, different form. And then the lack of overlap turned out the key concept of balance and overlap will continue to be actually prominent in Bayesian inference, even if on surface you look like, oh, I build a model, then I'm done. It's actually not that simple. And the last issue I didn't have time to touch is about identifiability, and there's no longer all or nothing, but it's rather a continuum between weak and strong identification. But that's for another day. And then, of course, we ask the question, why Bayesian if we already have such a good toolbox from frequentist domain? Why do we do this? So, of course, the usual arguments of Bayesian is like, well, I could give you autonomy qualification. I don't rely on large sample asymptotics, all that kind of thing. But specific to causal inference, what are the things we think that are useful? Is the first, probably most important thing is, the Bayesian framework. Within the Bayesian framework, you can deal with it. It's very natural. It's a unified framework to deal with all missing data. So you can impute all the missing potential outcome. And then based on that, you can basically allow straightforward inference of any causal estimate. So here I'm only talking about ATE, which is easier. But there are many estimates, much more complex, not for example, the principle of stratification specific causal effects and some other issues when you have categorical data. It's more complex. So but if you're Bayesian, you do causal inference, then all of this estimate can be done in the same way. And of course, when you in Bayesian, you have the automatic uncertainty quantification of any estimate. And because of that, you can easily combine this decision theory. You can have a utility function and then to do this dynamic decision making. That will be very helpful. And I would argue that Bayesian inference is particularly, Bayesian model in particular, suitable for complex settings. You know, when you have principal stratification, when you have sequential treatment or spatial and temporal, and it indeed has a full toolbox of models for this kind of situations, and that is very useful. So just final words, like both Bayesian, both design and analysis stage are central to causal inference. And this is the same for Bayesian as well as for frequentist. So a full Bayesian causal model by definition only involves the analysis stage, but proper Bayesian causal inference must take into account of the design stage. Must take into account of design, either of the two stages. So the ultimate goal in causal inference is to estimate causal effects. So the choice of the inferential mode, whether it's frequentist or Bayesian, is case dependent. So it's up to you to choose. Then, so my own feeling of this whole thing is for Bayesian, for causal inference, or perhaps anything in statistics, being Bayesian should always be a tool, not a goal. So that's it. And thanks. Thank to the people who keep the comments, and thank you for your patience. And the paper. These are the references. Sorry, I used a full hour.
Thank you, Fran, for the great talk. We received a lot of questions, but Peng have answered most of them. So Peng, would you like to choose a few important ones that you think Fran could answer publicly?
Let me review the old ones. Maybe Fran.
Can look at the new ones.
There are 4 questions left. Yeah, maybe you can answer some of them.
Oh, okay. So
yep.
this paper says some articles develop a general BART approach, allowing for different parametric priors on the error terms in some of the tree equation. Could a more general BART for priors in the BCF be useful? I guess, yeah. I mean, the Han himself recently wrote a paper recognizing the problem of the, this overlap issue. They actually, he wrote a paper basically use the local, the Gaussian process to do this local smoothing to overcome the issue in BART. So yes, I think that's definitely in the Bayesian. I think the Bayesian causal forest, the key idea is really not BART. BART is helpful, but the key idea is reparametrization. So then, if you based on that, that reparametrization, you can use as flexible as possible, whatever your favorite Bayesian way, as long as the computation is not too difficult. So yeah.
Maybe one more question then, and then we will finish up.
Yeah, so I'll go to the next. Could you give a more detailed explanation of why Bayesian is suitable for complex settings? Well, okay. So I don't have time here, but if you do say spatial statistics, and spatial statistics are almost like I think the most exciting development in that field is arguably Bayesian in the last 10 years or whatever. Bayesian, you have a vast amount of Gaussian process or car model, that kind of thing, from Bayesian perspective. And then you are, of course, how to combine that into Bayesian into causal is not straightforward. But you have this vast toolbox that I feel that in that complex, that kind of data set setting, you have Bayesian models toolbox you can use. I think the frequentists have less toolbox for that. So that's what I meant. and complex also, because you can basically deal with any causal estimand, right? I mean, so then even if you have complex estimand, you can also just use the Bayesian to do it in the same framework.
Yeah, another complex setting would be one with interference.
Interference, yeah.
Right, it's another, so assessing also the or quantifying uncertainty in causal estimands involving interference is also when units are organized in a network or and interfere on a network. It's not that easy from a frequentist perspective. And so the Bayesian offer a rather natural way of, you know, quantifying uncertainty there.
Yeah, so this is the same question. Like I saw Meng Li has a question, and that's related. It's asked like, you know, we see Bayesian causal inference is quite different from the frequentist counterpart. Do they converge in a non-trivial manner? Also to date, is there any problem that Bayesian is a better tool than frequentist? So again, as we mentioned, like in spatial and in interference, it just makes life easier. And also, I think they have some empirical examples to show that BART actually works really well, like better beat in this data competition. I think in the one ACIC conference that they do this blind data competition, and the BART actually outperform like the Bayesian causal forest and a lot of Bayesian frequentist approach. But do they converge in a non-trivial manner? I guess they converge. I mean, to me, the convergence is really, if you're good at design stage, you're kind of done. So, but other, I don't, yeah, I cannot think off the top of my head how do they converge in a non-trivial manner. And also, as I mentioned earlier, to incorporate those advanced models like spatial or temporal models or time series itself, it's not as simple as you just impose a Bayesian model and then say call the coefficient of a parameter, the coefficient of covariate, say this is causal effect. It's usually much more complex than that. So there are a lot of issues. Just a lot of things need to be done still there.
Great. Thanks, Fang, for a detailed answer. Thanks. So we'll start wrapping up now. If you don't mind, I'll share the end slides, which
Thanks everyone for your patience, and thanks to Peng and Fabric.
Yes, thank you. Yeah, thanks, Fang, for a very, very, very nice talk. And the slides and the talk are generally posted after a few days after this on our website. So for everyone asking, also if we didn't get to your question, or if you are wondering whether these questions will be passed on to the speaker and the panelists, they will. So don't worry about that. Everything posted in the Q&A gets forwarded to our speakers. Thanks, Fabrizio and Peng, for answering questions and discussing. Really appreciate that. And all right, so we hope that you'll all join us next week. Next week, we actually have a talk by Biwei Huang from UC San Diego on latent hierarchical causal structure discovery with random constraints. So yeah, we hope to see you all there. And thank you for coming today.
Thank you. Bye-bye.
Thank you.